Hello, class. We're now covering more advanced optimization models. The first class was linear programming. We call it LP. Now we move on to something called IP, which is integer programming. And that's when the solutions have to be integers. Integers means whole numbers, 0, 1, 2, 3, whole positive numbers. Before, we didn't care if we had a fraction of dollars or we didn't put a restriction that the number of units has to be integer. So we could have gotten a solution with decimal points, and that's acceptable in LP. Well, in integer programming in IP, we're saying this is not acceptable. And so that means adding more constraints to the problem, that the decision variables have to be integers. What did we say happens when we add more constraints to the problem? We make the problem more difficult. And this is why it takes more time usually to solve integer programming problems, IP problems, than it does LP problems. Now, it's not going to matter for problems we're doing in class because they're of a small nature. But when you get in the real world and you're solving much bigger problems, then you're going to see the limitation of solver, and solver is not going to be enough anymore, and you're going to have to go to a dedicated software for optimization. So the example that we're going to use for IP is employee scheduling or worker scheduling. So obviously, you don't want integers are not going to be acceptable, and so non-integer solutions will not be acceptable. You can't hire 1/3 of a person or 1/4 of a person. And so this is why we have to enforce the constraint that this person is, the decision variables representing these people need to be integers. Now, this problem, as described in your book, is select the optimal number of employees to work on each day or shift. And so, again, just like we did with the product mix problem, the simplest, most basic worker scheduling problem is what we're describing here. And so we have a need. We're a restaurant, we're an organization, a department in an organization. We have a need for a certain number of workers each day, Monday through Sunday, if we're working all shifts. So we have restrictions that if they start on Monday, they have to work 5 consecutive days. It's a union thing maybe, or even a non-union thing. We're working Monday through Sunday, but when somebody starts on Monday, they work 5 consecutive days, and then we have to give them 2 days off in a row. If you start on Tuesday, then you work Tuesday through Saturday, then you take Sunday and Monday off, and so on. So what are the inputs? Number of employees required each day, and employee salary. What do we pay them in case we are integrating that into the model? This basic model is number of employees required each day is going to be the only input. And so we get from management how many employees do they need Monday through Friday, Saturday, Sunday, and so on. The decision variables is the tricky thing in this model. So it's not just about modeling the problem, doing the nice layout. Sometimes there are modeling tricks, and the modeling tricks is what somebody before us has already discovered, a good way to model an employee scheduling problem, and from then on, maybe it's a person like me, a researcher in a university, they publish the article, they apply it, and then it makes its way to books, as you see in your book. So this is not something the author has done. It's somebody, a researcher, that came up with this application. And the trick in this model is in how you define the decision variables. How many decision variables do we need? We will look at when we look at the spreadsheet. Of course, what's the objective in this case is to minimize the number of employees or cost if we turn this problem into a cost. So no manager wants to hire more employees than is needed to fulfill the demand by day of the week. The constraints are labor, work restrictions, anything else like we talked about, work consecutive 5 days and then take 2 days off. So again, the question is, what do you recommend as an analyst? What type of model do you have to build to answer these questions? And so we go to the spreadsheet. The shell would look something like this. Again, whoever comes up with the model comes up with a solution. And so the solution would involve how do we model it in a spreadsheet, not just mathematically. So the key here is to lay out the spreadsheet like this, where you have room for decision variables, and those are the trick. How many people start on Monday? Not how many people do I need on Monday or Tuesday. It's not a product mix problem where it's like, okay, give me the good combination that would meet the demand every day. It won't work here. A product mix problem won't work here. The trick is we have to say that the decision variables are the number of employees starting their 5-day shift on Monday, the number of employees starting on Tuesday, the 5-day shift, and so on. This is your model. Right here is where we do the modeling. We write the formulas, and you're going to see how simplistic the formulas are. And right here is where the constraints are. So do I have on Monday all I need? I need 17 people, 13 people on Tuesday. I need different number of people each day. And so do I have what it needs? And then the total employees that I hire is going to be the total of the decision variables, because these people are starting at different days of the week. And so they're mutually exclusive. And so we sum this, and that's the total employees that we are hiring. We want to, in this case, minimize this objective function. We don't want to have more employees than we need. Again, if you were thinking about this problem from scratch and you didn't know that there is a model out there that somebody discovered, you would really have to scratch your head about this problem. What do I do? What's going to be my decision variables? It's not a product mix. It's not going to say, well, hire the addition of this. I mean, if we sum this, that's a very large number, you know? So you cannot just hire them. You're not hiring them for one day. You're hiring them for 5 days in a row. It would work to sum them if it was you're hiring people on a daily basis only, on a contract basis. Okay, then I need 1 of 5, but then there is no optimization model there. So it's kind of difficult to guess how many. Do I take an average? Well, that's not going to work with the constraints. You really have to scratch your head. And so unless you learn it in class or read it in a book or search it, you're not going to know how to do this. So we're going to jump to the solution here and show you. Now you're seeing familiar things. These are my decision variables. They're in pink. The only input in blue is the number of people I need each day. And the objective function is really the sum of these employees, you know, because like we said, they are mutually exclusive. This model is extremely simple, but only after you know how to do it. Okay, after somebody tells you how to do it and you learn about it. So how is that? The trick is in the decision variables. Just when do they start? And then the model itself is simple. Here is when you start, and here is when you're working horizontally. It tells you that. So you start on Monday and you have to work 5 days in a week consecutively. Then you're working Monday, Tuesday, Wednesday, Thursday, Friday, right? You're off Saturday and Sunday. So this cell is nothing but how many people started on Monday. So if I say 3 people will start on Monday, these 3 people will be available Monday, Tuesday, Wednesday, Thursday, and Friday, but not Saturday and Sunday. So that means if I start some people on Tuesday, let's say we start 4 people on Tuesday, these people will be available Tuesday to Saturday, and then Sunday and Monday, since this is the row, we roll back over, they're not available, they're off. So you repeat that for all, and again, all you're doing is carrying this formula. So it's B5, making it absolute, copying it to Saturday. Okay, here we did equal B4, make it absolute, carry it to Friday. And you do the same thing for all the rows. And then later on, I care about how many people are available on Monday to work. I need 17. So I care about the sum of this column. And so I sum this column, and I want it to be, in this case, greater than or equal to 17. Unlike the other constraint we've seen, which were less than or equal, we need a minimum of 17. So same here. This was one sum formula that I copied to the right, summing the column. And then later on in the constraints, we would set this whole range to be greater than or equal to this. The total employees is the sum of the decision variables, and that's again a sum. So the difficulty is not in the formulas here, it's how you set it up. Why did we put greater than or equal? Because something we didn't say earlier, it could be that if I put equal, I don't want to hire more people than is needed on those days, the model can come back and say it's infeasible. I cannot find you a solution here that meets all these constraints. So I expect some of these constraints to go above 17 and 13 and 15, especially that I'm not allowing fractions, I'm allowing integer solutions. And so, this is all there is in the spreadsheet model. We go to the solver to look at the solver model. Total employees, that's this cell. We want to minimize. The employees starting is this range, the pink range. And now we have employees available greater than employees required. That's this range is greater than this range. And this new constraint. And so how did I say that this range needs to be integer? When we come to add the constraint, we highlight this range, and we drop down, and we say int, which is integer. And that inserts this constraint. And we don't have to put anything in the right side. So that's what we did here. It's still simplex LP, it's just we're adding the integer constraints. That's what makes it an IP. Make the unconstrained variables non-negative. And if we click on solve, it gives us, 23 employees. And this is when they start. We see that Friday, nobody starts on Friday. It's not optimal to start anybody on Friday to work from Friday through Tuesday. And so we have 0, we have the number, and let's see, Monday is binding, Tuesday is binding. This one is not binding. I exceeded by 1. Same here, I exceeded by 1, and so on, because it would be infeasible if you try it and put this to be an equal sign. So it says here this problem has multiple optimal solutions, but the number of employees would say 23. And so management can find these multiple solutions. Every computer has a different numbering system, so the solutions you generate may look different. But it shouldn't exceed 23. And so these answers are integers. Why didn't we just do LP and then round the solutions? Because that doesn't give you an accurate optimal solution. You have that option, and some companies that have high demand on the number of constraints and decision variables may do that, but that will not necessarily be the optimal solution. This is by far the most optimal solution we can have. We can make use, actually, to our advantage, the fact that there are multiple optimal solutions that add up to 23. We know a lot of people like Saturday and Sunday off. Their kids are off school or whatever. So we will pick the solution, if we have multiple available, that will maximize the people that start on Monday, because Monday we have Saturday and Sunday off. And so, or we can rotate, or we can do different things. But this is how this example is run. And we can do solver table sensitivity analysis and say maybe we need more on Wednesday or Thursday. So we can change the range of an input cell and see the impact it has on the solution. But we'll do the sensitivity analysis in another video. Thank you.